Hi, welcome to this lecture on binary search trees. Here's the outline for this lecture. We'll first talk about a data structure called a binary search tree, or BST for short, and then we will discuss the implementation of the ordered symbol table API using a BST as the underlying data structure. And then we will talk about different ways of traversing a binary tree so as to systematically enumerate the nodes in the tree. And finally, we'll compare the performance characteristics of the different implementations in the symbol table API. Let's first start with the definition of a binary tree. So a binary tree is defined recursively as a data structure that is either empty or has a node with a key and an associated value and links to left and right binary subtrees. All right. So here is an example of a binary tree. So you have a node and that has pointers to at most 2 children. Okay? So this is an example of a binary tree. So each node has at most 2 children. All right. Now, a binary tree is said to be in symmetric order if each node's key is larger than all the keys in its left subtree and smaller than all the keys in its right subtree. So here is an example of a binary tree with symmetric order. So that's a binary tree, and we say it is in symmetric order if it has these keys, for example. So let's say 7 here, and then 2 here, so 7 is larger than 2, and then on this side we could have something like 15, and let's say 8 here, and then 17 here, right? So if you focus on any particular node, it is larger than the nodes on its left subtree and smaller than the nodes on its right subtree, right? And when that is the case for every single node in the binary tree, then we say that the binary tree has symmetric order. Now, a binary search tree, or a BST, is a binary tree that is in symmetric order. Okay. So here is an example of a binary search tree. So if you focus on, first of all, notice that it's a binary tree, meaning every node has at most 2 children, and it also has symmetric order. So if you focus on any particular node, such as this one, notice that its key is larger than all the keys in its left subtree, and it is smaller than all the keys in its right subtree. Okay, that's also true about this node. It's larger than all the keys on its left subtree, smaller than all the keys in its right subtree. Okay, so that's true about every single node here. So this is a binary search tree, right, or a BST. Now, how do we represent a binary search tree in Java? Well, we're going to represent it as a reference to a root node, okay, which consists of 5 fields. It consists of a generic key, a generic value, a reference to left subtree, which in itself is a node pointer, and a reference to the right subtree, which is also a node pointer, and it also stores, so each node also stores the number of nodes in the subtree that is rooted at that node. All right. So here is the Java code for representing a single node in a binary search tree. So it's going to be defined as a private class called node, and each node stores a generic key, a generic value, and node pointers to the left and right subtrees, and then n, which is simply the number of nodes rooted at that particular tree. Number of nodes in the subtree rooted at that particular node. Okay, and then here we simply have a constructor that can be used to build a node object given the key, the value, and the number of nodes in the subtree rooted at that node. All right. So let's take an example. So here we have 3-node binary search tree. So let's put some keys. So this could be, for example, E, this could be A, and this could be G, right? So this is a binary tree with symmetric order, so it's a binary search tree. And also, what would the values for left and right be for this particular node? Well, left is a pointer to that node and right is a pointer to that node. Okay, and then what are the values for n in each of these nodes? Well, here n is going to be 3 because that's the size of the tree that is rooted at that node. Here it's going to be 1 and here it's going to be 1. Right? And these guys don't have left and right subtrees. So left and right for this node and this node is simply null. Okay. All right. So that's how we represent a binary search tree in Java as a very simple private class called node. Now let's talk about implementing the ordered symbol table API using a binary search tree as the underlying data structure. So this implementation is called BST because it uses a BST as the underlying data structure. It stores generic key value pairs, and since it implements the ordered symbol table API, we make sure that the keys are comparable, right? So the keys have to be comparable, and only then you can implement the ordered operations. The instance variable is just a pointer to the root node in the binary search tree, and that's an object of type node that we just discussed in the previous slide. In the constructor, which we do nothing, so what this does is simply sets up an empty symbol table. Okay, we could have been explicit here and said root equals null. But that is unnecessary because when you declare root as such, it takes on a default value which is null. And then isEmpty makes a call to the size method and compares the value with 0 and returns true when the size is 0 and false otherwise. Size is an overloaded method. It returns the value returned by the private size method with root as the argument. Okay, so the private size method is right here. It takes a node and it simply returns the number of nodes in the subtree that is rooted at that node. And how does it do that? Well, it simply checks if x is null. If so, it returns 0. Otherwise, it returns the value of the field n in the node x. It simply returns the value of the instance variable n, right? Because that is the number of nodes in the subtree that is rooted at x. Okay, and so and these are all constant time operations. All right. Now let's talk about the get method. Well, get is also an overloaded method. We have the public get method from the API that takes a key as an argument, a generic key, and returns the corresponding value, or null if that key is not in the symbol table. And the way it does that is by simply returning the value that is returned by the private get method with root and key as its arguments. Okay, and here is the private get method. And this private get method implements binary search in order to look up this particular key. Okay, so let's see how it works. So here is one of the base cases where we say if x is null, simply return null to the caller. All right. Otherwise, what we do is we compare the given key with the key in the node, and if the given key is smaller, then we simply look for that key in the left subtree by making a recursive call to get on the left subtree. But if the given key is larger than the key in the node, then we look for the key in the right subtree by making a recursive call to get on the right subtree. Okay. Otherwise, if we are here, then we have a match. So the given key matches the key in the node, so which means that the given key is in the symbol table, so we simply return the corresponding value. Okay, so this is another base case. And that is your classic binary search, right? Now, what is the running time of get? Well, it basically depends on the height of the tree, and we will talk about that later, all right? Now, let's talk about the contains method. Well, contains is easy once you have get in place. So we simply make a call to get with the given key as an argument, and if that comes back with a non-null value, we return true, saying that the key is in the symbol table. Otherwise, we end up returning false. And what's the running time of contains? It's the same as the running time of get, okay, which we said is the height of the tree. Now let's talk about the put method, which is also implemented as an overloaded method. So we have the public put method from the API that takes a key and a value as arguments. And the first thing that we do is check if the value is null. And if so, as per our convention, we treat it as a delete operation. And we remove the key and the associated value and simply return. Otherwise, what we do is we make a call to the private put method, giving it the root as the first argument, the key as the second argument, and the value as the third argument. And whatever is returned by put is assigned to the root. Okay. So this put here, when it's done, it simply returns a reference to the root of the binary search tree, which we assign to the variable root. So now let's talk about the private put method, which is recursive. So here is a base case where we say if x is null, simply return a new node object with the arguments key, val, and 1. So what does it mean for x to be null? It means that the given key and value, the given key was not found in the symbol table. So in that case, we build a new node for it in the binary search tree with this key and this value, and with n set to 1, because this is a new node, and the number of nodes in the subtree rooted at that node is just 1. Okay, so that's that. Otherwise, what we do is, if x is not null, we compare the given key with the key in the node. And if the given key is smaller, we try inserting the given key value pair in the left subtree by making a recursive call to put. And put eventually returns a reference to that subtree, which we assign to x dot left. Okay. But if the given key is larger than the key in the node, then we try inserting the key value pair in the right subtree of x by making a recursive call to put on the right subtree, and then put eventually returns a pointer to the right subtree, which we end up assigning to x dot right. Right? Otherwise, if you're here, then there is a match on the key. So the given key matches the key in the node. In that case, as per our convention, we simply update the current value in that node to the given value. Okay, and then in here we update the node counts. We say that x dot n, the new value for n in x, is simply 1 for itself, and then plus the size of this the left subtree plus the size of the right subtree, and then finally we simply return x to the column. Right, so that's how put works. So let's trace the put method for an example. So let's say the client program makes a call to put with the arguments e and 42. Okay, so the key is e and value is 42. And initially root is null. All right, so how does this work? Well, this put was called with key set to e and val set to 42. So val is not null, so we end up making a call to the private put method, giving it root, which is null at this point, and e for key and 42 for val. So this results in a call to the private put method with null as the first argument, and then e and 42 as the next two arguments. Okay, and how does that work? Well, we are here in the base case, so x is null, so that simply returns a new node to the caller. Okay, so a new node is established with the key e, value 42, and n is set to 1, right? And this node is returned to its caller, but who called put? It was the public put method. And what does the public put method do? Well, it takes that reference to that node and assigns it to root. So that's how you get root pointing to that particular node that we just created. Okay, so we now have a binary search tree with one node in it. Now let's say the client goes about calling put with the arguments a and 31. So how does this work? Well, this results in a call to the private put method with the root as the first argument, and then a and 31. But now the root is not null, so x is not null, so we end up here and we compare the given key a with the key in the node, which is e. So how does a compare with e? A is smaller, so we end up here. So what are we doing here? So we say we try to put the given key value pair in the left subtree of root. So, but the root currently has no left subtree, so this is going to result in the recursive call put null a and 31, right? So how does this call work now? Well, here we are at the base case, so we simply return a new node. So this creates a new node with the key a, with the value 31, and n is set to 1. Okay, and so that's what this put method returns to its caller, which is this guy. So what does this put method do when this guy comes back? Well, it simply assigns the return value to x dot left. What was x there? X was root. So that's how we get the left pointer of root set to this particular node that we just created. Okay, so that line is now done, and we end up here. So now we say the new value for n in x, which is the root at this point. So the new value for n is 1 for itself plus the size of the left subtree. What is the size of the left subtree? Well, it is 1 plus the size of the right subtree of the root, which is 0. So this is now 2. Okay. So the value of n at the root has been updated, and we simply return x to the caller. X, which is the root, is returned to its caller, which is this put method, the public put method, and that simply assigns that reference to root. So now root is pointing to this 2-node binary search tree. All right. So I would strongly encourage you guys to try some more examples. Try inserting a few more nodes into this binary search tree, and also try inserting a key value pair where the key is already in the symbol table. Okay, so that will give you some good practice on how these functions work, and especially it will give you a good handle on how recursion works here. Okay. Now the shape of the binary search tree depends on the order of insertion of the keys. Okay, and what you see here is the best case scenario for the tree shape, because in this case the tree is perfectly balanced. And what that means is that if you focus on any particular node, that node has as many elements in its left subtree as it has in the right subtree. Okay, so in this case, when you go search for an element, you you can perform that operation very efficiently, because the height of the tree is very shallow, right? Here is the typical case scenario where the keys arrive in random order, and your binary search tree is more or less balanced. So here again, when you're looking for a particular key, you can perform that search quite efficiently, right? Because the height of the tree here is fairly shallow as well. And the worst case scenario is what is shown here, where the height of the tree is basically the number of elements in the tree. And when do you get a tree like this? You get a tree like this when the keys arrive in either ascending or descending order, right? So if your incoming keys have this ordering, and if you go about building a binary search tree with these keys, you will get something like this, which is really not a binary tree. It's basically a linear structure, right? So in this case, when you go about looking for a particular element, in the worst case, you perform n comparisons, where n is the number of elements in the tree. So in the worst case scenario, the search operation just deteriorates to a linear time operation. And in the best case scenario, it is logarithmic, because you perform a binary search on a binary search tree whose height is approximately log of n. So the number of comparisons for search or insert in a general binary search tree is approximately the depth of the node. All right, and if n distinct keys are inserted into a binary search tree in random order, then the average number of comparisons for search or insert is approximately log of n. All right, so that's when you're either in the best case or the typical case, right, where the tree, the binary search tree, is either perfectly balanced or more or less balanced. Whereas in the worst case scenario, the number of comparisons for search or insert is approximately n. Okay? Because in the worst case scenario, things deteriorate to linear time algorithms. So here is a typical BST that results from inserting 256 random keys. Right? So these keys arrive in no particular order. So when you build a binary search tree out of those keys, which arrive in no particular order, you get a tree which is more or less balanced. All right? So that's what you see here. Now let's talk about implementing the ordered operations from the simple table API. We'll start with the minimum and the maximum operations. So given a binary search tree, where do you find the smallest key and where do you find the largest key? Well, in order to find the smallest key, you start at the root and you go all the way to the left until you find a node that doesn't have a left child. Okay? And then the key in that node is basically the smallest key. And where do you find the maximum? Well, you start at the root and you go all the way to the right until you find a node that doesn't have a right child or a right subtree, and that the key in that node is the largest key. Right? So that's how you find the minimum and the maximum, and here are the corresponding implementations. So minimum is implemented as an overloaded method, that is the public minimum method, which simply returns the smallest key. So we first check if the tree is empty, and if so, we return null. Otherwise, we make a call to the private min method, giving it the root as the argument, and that method returns the node that contains the minimum key. And then this method here simply pulls the key out of that node and returns that, right? So how does the private min method work? Well, it receives a node as an argument, and what it does is it's a recursive implementation that returns a node that contains the minimum key in the binary search tree that is rooted at that node. Right? So how does the implementation work? Well, the base case says if x doesn't have a left child, simply return x to the caller. All right? So for example, in this case, when we arrive at this node, we don't have a left child, so we simply return this guy to its caller, right? Otherwise, what we do is we make a recursive call to min on the left subtree, okay, and return that value to the caller. So that's saying that we need to keep going all the way to the left until we find a node without a left child. Okay. So that's the implementation for min. What about max? It's a similar idea. So we have the public max method, which first checks if the tree is empty, and if so, it returns null. Otherwise, it makes a call to the private max method, giving it the root as an argument. And the private max method simply returns a node that contains the largest key. And here we simply pull out that key from that node and return that. Okay? And the private max method is recursive. We first check if the right child is null, and if so, we return x to the caller. Otherwise, we make a recursive call to max on the right subtree and return that value to the caller. Okay? So here we are saying keep going all the way to the right until we find a node that doesn't have a right child. All right? So that's how we implement min and max. Now let's talk about the floor and ceiling operations. So recall that the floor of a given key is the largest key in the symbol table that is less than or equal to the given key. All right? And the ceiling of a given key is the smallest key in the symbol table that is greater than or equal to the given key. Okay, so those are the definitions for floor and ceiling. So how do we compute the floor? Well, here there are three cases to consider. Okay, so let's say we are computing the floor of a key k. So the first case says if that key equals the key in the node that we are currently looking at, then the floor is simply that key itself. Okay, so that's case 1. Case 2 says if the given key is smaller than the key in the node, then we need to look for the floor of the given key in the left subtree. All right? And the last case says that if the given key is larger than the key in the node, then we need to look for the floor of the key in the right subtree. And if we find such a key, meaning if there is a key that is less than or equal to k, the given key in there, then we return that as the floor of the given key. And if we don't find such a key, then we simply return the key in the node itself. All right? So those are the 3 cases. So let's look at an example. So let's say this is our binary search tree and we are asked for the floor of G. So what do? Well, we start at the root. How does G compare with S? Well, G is smaller than S, so we are in case 2. Okay, so in that case, we go look for the floor of G in the left subtree of S. So we look for it here. Okay, so here again, what do we do? Well, we compare G, the given key, with the key in the node. Well, G is larger than E, so we are in case 3. So we go look for the floor of G in the right subtree of E. Okay, meaning we are looking for an element that is less than or equal to G in the right subtree of E. Well, we don't find such a key here because all these guys are larger than G. So what do? Well, this case says that in that case we simply return the key in the node as the floor, so we say the floor of G is E. Okay, so convince yourself that this algorithm computes the floor of D as C. Okay, that's a good exercise. So I encourage you guys to do that, and then also convince yourself that the ceiling of Q is R. So that's the smallest key in the symbol table that is greater than or equal to the given key Q. Okay, so work these out as exercises. All right, so now let's look at how we implement these 3 cases in code to calculate the floor of a given key. So floor is implemented as an overloaded method. So we have the public floor method that takes a key as an argument, and it simply calls the private floor method, giving it the root as the first argument and the key as the second argument. And then if floor comes back with a null, we simply return null, saying the given key has no floor in the symbol table. Otherwise, we simply pull out the key from X and return that as the floor. Okay. Now let's look at the private floor method, which is where we implement these 3 cases. So we are given a node X and a key. So what do we do first? Well, we check if X is null. If so, we simply return null to the column. Otherwise, we compare the given key with the key in the node, and if we have a match, then we are in case 1 and we return X to the column. Okay. And otherwise, if the given key is smaller than the key in the node, then we look for the floor in the left subtree. So this is case 2. Okay, and that amounts to a recursive call to floor on the left subtree. Otherwise, the given key is larger than the key in the node. So in that case, it's possible that the floor of the given key is in the right subtree. So we look for it in the right subtree by making a recursive call to floor. And that comes back with some node T. And if that node T is not null, then that means that we actually found a floor in the right subtree. So we simply return T to the column. Okay. Otherwise, if T is null, then we say that the floor of the given key is in the node itself. So we return the node itself to the column. Okay, so that's how floor is implemented. What about ceiling? Well, it's a similar idea. So let's say we are computing the ceiling of the key K. So here again, there are 3 cases to consider. If the key equals the key in the node, then we simply return the key itself as the ceiling, right? Otherwise, if the given key is larger than the key in the node, then we look for the ceiling of that key in the right subtree. Okay? Otherwise, if the given key is smaller than the key in the node, then we look for the ceiling of the key in the left subtree, if there is any, to find if there is any key that is greater than or equal to k in the left subtree, and if we find one, that is the ceiling. Otherwise, we simply return the key in the node itself as the ceiling. Right? So as you can see, it's a similar idea to the floor of a key. And here is the implementation. So it's also implemented as an overloaded method. So the public ceiling method calls the private ceiling method, giving it the root and the key as arguments, and that comes back with a node object, which if it is null, we simply return null to the caller, saying that there is no ceiling for the given key. Otherwise, we simply pull out the key from the node and return that as the ceiling of the given key. Now let's look at the private ceiling method, which receives a node and a key as arguments. We first check if the node is null. If so, return null to the caller. Otherwise, we compare the given key with the key in the node. If there is a match, we simply return the node itself. That's case 1. If the given key is larger than the key in the node, we look for the ceiling in the right subtree by making a recursive call to ceiling on the right subtree. So that's case 2. And if the given key is smaller than the key in the node, then it's possible that the ceiling of the given key is in the left subtree. So we go look for it by making a recursive call to ceiling on the left subtree. And if that comes back with a node that is not null, then we know that we found the ceiling in the left subtree. So we simply return that node. Otherwise, if t is null, we say that the ceiling is the node itself. Right? Or the ceiling is contained in the node itself. So we just simply return x to the column. Right? So that's how we implement the ceiling operations. Now let's talk about rank and selection operations. So recall that the rank of a given key is the number of keys in the symbol table that are strictly less than the given key. Right? That's the definition of rank. And select is the opposite of rank. So select takes a rank as an argument and returns a key in the symbol table that has that for the rank. All right? So let's see how we first implement the rank of a key. So rank is implemented as an overloaded method. So we receive a key as an argument, and we simply return the value that is returned by the private rank method with key and root as its arguments. Okay, so let's see how the private rank method works. Well, we first check if the node x is null, and if so, we simply return 0 to the caller. Right? Otherwise, so that's one of the base cases. Otherwise, what we do is we compare the given key with the key in the node, right? And if the given key is smaller, then we simply return the value that we obtain from a recursive call to rank on the left subtree. Okay, so we do that when the given key is smaller than the key in the node. All right. Otherwise, if the given key is larger than the key in the node, then what we say is that we simply return 1 for the node itself plus the size of the left subtree, okay, plus whatever is returned by a recursive call to rank on the right subtree. So what are we saying here? We're saying if the given key is greater than the key in the node, then the key in the node clearly contributes something to the rank. So that's this one here, because that key is smaller than the given key, right? And then it is also true that every key in the left subtree of x is smaller than the given key. So we add all that to the rank, right? And then it's also possible that there is a key in the right subtree that is smaller than the given key. So we look for such keys in the right subtree via this recursive call. Okay, so this expression should make perfect sense. And we do this when the given key is larger than the key in the node, right? Otherwise, we have a match, in which case we simply return the size of the left subtree, right? Because if we have a match, then every element to the left of the current node is smaller than the given key, Okay, so we simply return the size of the left subtree to the caller. So that's how we implement rank. All right. So now let's look at the select method. So select is also implemented as an overloaded method. So we get a rank as an argument, and we are supposed to return a key in the symbol table that has that for the rank. Right? Meaning we are supposed to return a key in the symbol table that has these many elements that are strictly less than it. All right. So what we do is we first check if k is within bounds. So if k is negative or k is greater than the size of the binary search tree, we simply return null. All right. Otherwise, what we do is we make a call to the private select method, giving it the root as the first argument and k as the second argument, and that's going to come back with a node object, and then we simply return the key in that node object. Right. So now let's look at the select method. So here we are given a node and a rank k. So we first check if x is null, and if so, return null to the caller. So that's one of the base cases. Otherwise, what we do is we ask for the size of the left subtree, and we call that t. So we are currently focusing on node x, and we get the size of its left subtree, and we call that t. Now, if t is greater than k, okay, then what does it mean? It means we are overcounting. All right. So in that case, what we do is we simply make a recursive call to select on the left subtree. Okay, so that's that. Because in this case, we have clearly overcounted when t is greater than k. Right. Otherwise, if t is less than k, then it would mean that we have undercounted. There still might be some keys that we have not accounted for, okay, because t is short of k. So what do we do in that case? Well, we make a recursive call to select on x dot right. So the number of keys in the left subtree is not enough. It fell short of k. So we go look for the remaining keys in the right subtree. Okay, and how many such keys do we look for? Well, it is k minus t minus 1. Right? Why k minus t? Because that's the shortfall, right? And y minus 1, that's for the node itself. Okay, so we go look for that difference in the right subtree. So that's that. And if we have a match, then we simply return the node itself to the caller. Okay, so that's how we implement select. Let's now look at some examples of rank and select. So let's say we want to calculate the rank of E, right? So the key is E. So we need to know how many keys in the symbol table are strictly less than the given key E. So how does rank work? Well, so this rank is a call to the public rank method that results in a call to the private rank method with the key E as the first argument, and the node initially is going to be the root itself. So this is the root. Okay, so let me just write S for the root because that's what we have at the root. So what do we do in that case? Well, we check if x is null or not. Well, it's not. So we compare the given key with the key in x. So we compare E with S. E is smaller, so this results in a recursive call to rank on the left subtree. Okay, so this becomes a call to rank with E as the first argument. And what is the left child of S? Well, that's E. Okay, so what happens then? Well, here again, x is not null, so we end up comparing the given key with the key in the node. So now we have a match, so we are here. So what do we return in this case? Well, the size of the left subtree of x, which was E. What is the size of the left subtree of E? Well, it is 2. Okay, so this guy returns 2 to its caller, right? And what does that do? That returns 2 to its caller. Okay, and then this guy returns 2 to the client. And is that correct? Well, absolutely, because how many keys do we have in the symbol table that are strictly less than E? Well, we have 2 of them. We have A and C. So this is the correct result, right? So that's rank. Now let's talk about select. So let's say we ask for select of 2. So we want to know what is the key in the symbol table that has 2 for its rank. Okay, so let's see how that works. So that's a call to the public select method with 2 as an argument. That results in a call to the private select method with a root as the first argument, and the second argument is 2. And here, so root is not null, so we get the size of the left subtree of x. Well, what is the size of the left subtree of x, where x is the root? It is 6, right? So t is going to be 6. We compare 2 with 6. 2 is strictly less than 6, so we are here. So we simply return a recursive call to select on the left subtree of root, which is e, with k2. Okay, now what happens? Well, x is not null because we are looking at a node e. So what do we do in that case? We ask for its left, the size of its left subtree. What is the size of the left subtree of e? Well, it is 2, right? So that is 2 now, and k is 2. So we are here, we have a match. So what does this guy do? It simply well, so now we have a match because t is the same as 2. So this simply returns x, which is e to its caller. So this guy returns the node e to its caller. That ends up returning the node e to its caller. Okay, and this select method returns e to the client, right? Is that correct? Well, absolutely, because e is the key in the symbol table that has 2 for its rank, or in other words, e has 2 keys that are strictly less than it. Okay, so that's how rank and select behave. So now let's talk about the range count and range search operations. So let's start with size. So size is supposed to return the number of keys in the symbol table that are between low and high, right? Both inclusive. So what do we do first? Well, we first compare low with high. If low exceeds high, we simply return 0 because there is nothing between the two in that case. Otherwise, what we do is we check if high is actually in the symbol table. If so, we return the size as the rank of high minus the rank of low plus 1 for itself. Okay, so that's that. And if high is not in the symbol table, we return the size as the rank of high minus the rank of low. Right? So that's how we implement size. Now let's look at the keys method. So there are two versions of the keys method. One that returns all the keys in the symbol table, okay, in sorted order, and the other one that returns the keys in the symbol table that are between low and high, both inclusive and in sorted order. So let's first look at the first keys method. So the first keys method simply relies on the second one, right? So assuming that we have this keys in place that returns the keys between low and high, then implementing this one is trivial because we can simply say low is the smallest key in the symbol table and high is the largest key in the symbol table. Okay? So when these are the arguments, we end up returning all the keys in the symbol table as an iterable object. So now let's focus on this other keys method. So here we are supposed to return an iterable object that contains just the keys between low and high. So we start with an empty queue, and then we make a call to this private keys method, okay, which is what is shown here, giving it the root as the first argument and this empty queue as the second argument, low third argument and high as the fourth argument. Okay, and this initially empty queue is going to be populated by this method keys with the keys that are between low and high, and then at the end we simply return that queue to the caller. Okay, so let's see how the private keys method works. So if x is null, we simply return onto the caller, right? Otherwise, what we do is we compare low with the key in the node and call that CMP low, and we compare high with the key in the node and we call that CMP high. Okay, now if CMP low is less than 0, what it means is that low is less than the key in the node. In that case, we recursively call keys on the left subtree of x. Okay. Otherwise, if CMP low is less than or equal to 0, meaning if low is less than or equal to the key in the node, or CMP high or high, in other words, is greater than or equal to the key in the node, we enqueue that key into the queue. So this is where we actually populate that queue, okay, with the key. Otherwise, if so that's also a base case. Otherwise, what we do is we if high is greater than the key in the node, then we simply make a call to keys recursively on the right subtree. All right. So what we're doing here is basically traversing the tree and collecting the keys that are in the range low through high. And where are we collecting them? We are collecting them in this queue that is given to us as an argument. Okay. So that's how we implement range count and range search. Now let's talk about how we implement the deletion operations. Right? So let's start with deleting either the minimum or the maximum key in the symbol table. So how do we delete, let's say, the minimum key? Well, we know where to find the minimum key. We need to go all the way to the left until we find a node that has no left child, right? So what we do is we go left until we find a node with null left, meaning no left child. And then we replace that node by its right link, because that node might still contain a right child. So we simply replace the node with the right child, right? And then we update the tree counts because we are taking a key out of the symbol table, right? So that's what we do to delete the minimum. What about delete the maximum? Well, it's the opposite. We go all the way to the right until we find a node with a null right link, meaning we go all the way to the right until we find a node that doesn't have a right child, and then we replace that node with any left child, okay, because that node might still contain a left child. So we replace the node with a left child and we update the tree counts. Okay, so that's how we implement delete min and delete max. So let's look at the code. So delete min and delete max both are implemented as overloaded methods. So we have a public delete min that first checks if the tree is empty. If so, it returns, it throws an exception. Otherwise, it makes a call to delete min on the root and assigns the return value to root. So delete min will remove the minimum key from the binary search tree and return a reference to the root, which is what is assigned to root. Okay. Now let's look at the private delete min method. So we are given a node here, and then we check if its left child is null. If so, we simply return the right child to the caller. Okay, so this is where we are replacing the node with the right link, right? And then we say, but if that's not the case, we say make a recursive call to del min on the left subtree, okay, and assign the return value, the reference, to x dot left. So in this case, we're saying keep going to the left, right? So that's what we're saying here. And then this is where we update the tree, the subtree counts. So we say that the value for n now at x is simply the size of the left subtree rooted at x plus the size of the right subtree and plus 1 for the node itself. Okay, and simply return x to the caller. So this is, in this line is where we handle this part. and then this is where we keep going all the way to the left, so that is bullet number 1, and this is where we update tree counts, so that's bullet number 3. Okay, so that's how we implement delete min. Delete maximum is a similar idea. The public method first checks if the tree is empty, if so throws an exception, otherwise it makes a call to the private delete max method and assigns the value returned by that guy to the root. Okay, and the private delete max method checks if the right subtree of x is null, if so simply returns a pointer to the left subtree. Right, so that's so this implements bullet number 2. Right, otherwise what we say is keep going all the way to the right, so that's implementing bullet number 1. And then finally we update the tree counts. We say the size of the tree rooted at x is simply the size of the left subtree plus the size of the right subtree plus 1 for the node itself, and then return x to the column. Right, so this is where we update tree counts. Okay, so that's delete min and delete max. So now let's talk about how we delete an arbitrary key from the symbol table. All right, so let's say we want to delete a node with the key k. And the algorithm that we're going to discuss here is called Hibbard deletion algorithm, right? So we want to delete an arbitrary node with the key k in it. So what do we do first? Well, we search for the node that contains that key. So let's call that node t. Okay, so for example, if this is your binary search tree, and if you want to delete the key e, what do? Well, we first search for it using binary search. So we start at the root, and then we compare e with s. Well, it is smaller, so we go to the left and we stop there because we have a match there, and that's the node that we call t. Okay, so that's what we're saying here. First search for the node t that contains that given key k. Okay, now there are 3 cases to consider. The first case is where that node that you want to delete has no children. Okay, and that's the easy case. We can simply delete t by setting the parent link to null. Right, so that's what we do when that node has no children. But what if that node has exactly one child, a left or a right child? So in that case, what we do is we delete the node t by replacing the parent link with that particular child, either left or right. So that's also an easy case. But what if the node that we want to delete, the node t, has 2 children? Okay, so in that case, what we do is we find what is called the successor x of t. Okay, so the successor is basically the smallest element that is larger than the key in the node t. Okay, and we call that key x. Right, and x has no child, left child by definition. Okay, so we find the successor x of t, and then what we do is we delete the minimum in t's right subtree, okay, and put x, which was found here, the successor, in t's spot. Okay, and when we do that, we have not only deleted the given key and the associated node, but we've also made sure that the resulting tree is in symmetric order, meaning it is a binary search tree. All right. So, and then finally we update tree counts because we have taken a key out of the symbol table. Right. So let's look at an example. So let's say we want to delete e from this binary search tree. Well, we first find it using binary search. We call that node t, and now we find the successor x of t. Why are we in this case? Because this node has 2 children, right? So we are in case 3. So we find the successor x of t. What is its successor? Well, it's basically this node here, because that is the smallest key in the symbol table that is greater than e. That's the successor. All right, and we call that x. And then what we do is and the way we find the successor is by making a call to the min method on the right subtree of t. So that's what is shown here. So that's how you find the successor. Okay, and then what we do is we delete the minimum in t's right subtree. So we make a call to del min on t dot right. Okay, so that what does that do? Well, that we know it's going to remove the minimum key in this tree, which was h, right? That's the smallest key. It's so that's taken out. M takes its spot, and del min simply then returns a reference to the tree itself. So it returns a pointer to this guy. Okay, so del min returns that. And then what we do is we simply put x, which was the successor, in t's spot. So this guy, which was the successor, takes t's spot. So it ends up there. Okay. And what is the left child of x? Well, left child of x is simply whatever the left child of t was, right? So in the end, what we have is this binary search tree. Notice that key E is gone, and what we have as a result is a valid binary search tree, right? And notice also that the tree counts have been updated. Okay. All right, so the algorithm again, when we have two children associated with the node that we want to remove, the algorithm says first find the successor x of that node, okay, successor x of that node, and then delete the minimum in t's right subtree and simply put x in t's spot, right, and then update tree counts. So now let's look at how this is done in code. So here again we have delete as an overloaded method. So we have the public delete method that takes a key that we want to delete as an argument, and it makes a call to the private delete method, giving it the root as the first argument and the key as the second argument. And this guy is simply going to return a reference to the root, which is assigned to root. Okay, so let's see how the private delete method works. Well, we first check if x is null, and if so, return null. There's nothing to be done in that case. Otherwise, what we say is we compare the given key with the key in the node. Okay, if the given key is smaller, then we go about deleting the given key in the left subtree. So that's this recursive call, and we assign the return value to x dot left. Otherwise, if the given key is larger than the key in the node, we go about deleting the given key in the right subtree. Okay, and we assign the return value to x dot right. So this is binary search. We're basically trying to find the key that we want to delete, right? And if we end up here, what do we know? Well, we have a match on the keys, right? So we are basically looking at the node x that contains the key that we want to delete. So in that case, what we do, we first check if x dot right is null. Okay, so this is where we implement those three cases. So if x dot right is null, we simply return x dot left to the column. Okay, and if x dot left is null, we simply return x dot right to the column. All right, so these are the cases where the node that we are trying to delete has no children, or just exactly one child, right? So those are handled here. If we end up here, what that means is that we are looking at a node that has two children. Okay, this is case 3. So in that case, we say that t is simply x, whatever x is. So t is pointing to what x is pointing to, and then we go about finding the successor. So x is simply a call to min on the right subtree. So this is going to find the smallest key that is greater than or equal to that is greater than the given key. That's the successor. Okay, and then what we say is x dot right is simply whatever is returned by a call to del min on t dot right. So this call here will remove that a successor, right? And it will return a reference to that modified right subtree, which we assign to x dot right. Right? And then we finally say x dot left is simply t dot left. Okay, so the left subtree of x is whatever t's left subtree was. right? And then finally here we update the tree counts. So we say that the size of the tree rooted at x is simply the size of the left subtree plus the size of the right subtree plus 1 for the node itself, and return x to the column. Okay, so that's how we implement Hibbert deletion algorithm. So now let's talk about how we systematically traverse a binary tree, right? Or in other words, how we systematically enumerate the nodes of a binary tree. So there are different traversal schemes, and we're going to explore 3 different traversal algorithms, right? So the first traversal algorithm is called pre-order traversal, and the way that is implemented is as follows. So we have a public pre-order method that simply calls the private pre-order method on the root. Okay, and the private pre-order method is recursive, so it takes a node x as an argument, and the base case says if x is null, simply return, right? Nothing to do. Otherwise, what we do is we process that node. And by process, we mean we do something with that node. And one example of that might be to simply print the key in that node. Okay, so that's a process. So we take the key in that node and simply print it. Okay? And then what we do is we make 2 recursive calls, first on the left subtree of x and then on the right subtree of x. Okay, so what is important here is to notice that the processing step happens before the 2 recursive calls, and hence the name pre-order traversal. Okay, so here the processing happens before the recursive calls. Another traversal mechanism is called in-order traversal. So here we have a public in-order method that calls the private in-order method with the root as the argument. And the private in-order method gets a node x, checks if that node is null, if so simply returns. Otherwise, it makes a recursive call to in-order on the left subtree, and then it processes the node that might be something like printing the key in the node, and then it makes a recursive call to in-order on the right subtree. And here what is important to notice is that the processing step happens between the 2 recursive calls. It's sandwiched between the 2 calls. Okay, and finally we have a post-order traversal mechanism where the public post-order method calls the private post-order method with the root as the argument, and the private post-order method receives a node and checks if the node is null, and if so returns to the caller. Otherwise, it makes 2 recursive calls to post-order on the left and the right subtree, and then processes the node itself. Okay, so here again notice that the processing step happens after the 2 recursive calls, and hence the name post-order traversal. Okay, so what is different in these 3 traversal mechanisms is that is the place where the processing is done. In the first case, the processing is done before the recursive calls. In the second case, the processing is done between the recursive calls, and in the third case, it is done after the recursive calls. Okay. So each of these 3 traversal mechanisms, it's going to enumerate the nodes in the binary tree in different order, right? And if you have the binary tree as a binary search tree, and if you perform an in-order traversal, which is this guy here, on a binary search tree, then the nodes come out in ascending order. Okay, that's an interesting thing to keep in mind. So if your tree is actually a binary search tree, meaning it has keys like 5, 2, 1, and 7, so that's a binary search tree. So let's throw in another element, 6. So that's a binary search tree. So what we are saying is, if we enumerate or if we traverse this tree in order, then the keys are going to come out in sorted order. Okay. In other words, if you want to print out the keys of a binary search tree in sorted order, a nice way to do that is to simply do an in-order traversal of that tree, right? So let's now look at a concrete example of a binary search tree and see how the 3 traversal mechanisms enumerate the keys in the binary search tree. So here's an example of a BST, and so pre-order, in order, and post order are going to enumerate this tree in this order here, right? So let's say that the processing step simply involves printing the key in the node. So why are we seeing this output with pre-order traversal? Well, how does pre-order work? We first call it on the root, and then we process the node. Well, we say that we just said that processing involves printing the key, so we end up seeing S, right? And then we make a recursive call to pre-order on the left child, which is E, and that in itself is going to simply process the node, meaning print it. So that's how we see an E. And that makes a call to pre-order recursively on its left child, which is this guy here, which prints the node A. That will end up making a call to pre-order on the left child, but there is nothing there, so we are back up here, right? And then what pre-order will do here is make a call to pre-order on the right child. Okay, that's how we end up seeing this. And then we make a call to pre-order on the left, but there is nothing there. Pre-order on the right, there is nothing there, so we are back up here. And this guy now returns, so we are back up here, and we make a call to pre-order on the right right subtree of this guy, which is that, and that's how we end up seeing R. And then we make a call to pre-order on the left subtree, which is H, which is how we get that. There is nothing to the left of that, but now we make a call to pre-order on the right, so we end up getting that. There is nothing to the left or right of M, so we are back up here, and then we are back up here. There is nothing to the right of that, so we are done with this node as well. We come here, we are done with that node, we are here, and now we simply make a recursive call to pre-order on the right subtree of S, which is X, which ends up printing X. Okay, and we are done with this node. We go back here, and we are done with the whole tree. So that's how you get this particular ordering via a pre-order traversal of the tree. What about in order? Well, we start at the root, and then here, remember that we first make a recursive call to the left subtree. Okay, so we make a call to this guy. And what does that do? That makes a recursive call to in order on the left subtree. So we end up here. That ends up making a call to in order on the left subtree, but that returns right away because it's null. So we come here, but then what does in order do? It does the processing step. So it's going to print the key, and that's how we get A here. And then it does a recursive call to in order on the right subtree, which is this guy. And here we're going to make a call to in order on the left subtree, which is null, so that returns, and then we end up processing the node, meaning we print the key, and then we make a call to the right subtree, which is null, so we are done with this guy, and then we are also done with this. Now we go back up here and we process the node, so we end up printing E, and then we make a call to in order on the right subtree. Okay, and that in itself will result in a call to the on the left subtree, which will result in a call on its left subtree that returns right away, and we end up processing or printing this key, which is H. Okay, and then we make a call to in order on the right subtree, which ends up calling in order on the left, but that returns, we end up printing M, and then a call to the right, which returns, and so we are done with this guy, we are done with this as well. When we come here, we end up printing it, and then we make a call to in order on the right, but there is nothing there, so that returns, and then we come back here, we are done with this guy, we come back here, we print it, and then we make a call to in order on the right subtree, okay, which ends up calling in order to the left, but that returns, then we process the node, we print X, we call in order on the right, that returns, and then this guy returns here, and now this guy returns as well because we are done with the whole tree. Okay, so that's how we get this ordering. And notice, as we said before, if your tree is a binary search tree and if you traverse it in order, we get the keys in sorted order. So these are all the keys in the BST, but they are in sorted order, right? What about post order? Well, here again we started the root, but now we first make a call to the left subtree, and then we make a call to the left subtree from there, but there is nothing there, so we return. And then we make a call to the right subtree. Okay, so we go here, we make a call to the left, that returns, make a call to the right, that returns, and then we end up printing the key. So that's how we see C. Okay, so now we are done with this node. We go back here, and we simply end up printing A. Okay, so we are done with this node. So we go back here, and now what do? Well, we visit its right subtree. So make a call to post order on the right subtree, which ends up making a call to post order on its left subtree, which ends up making a call to post order on its left, but that returns a call to post order on its right, and then that it makes a call to its left and right, which return, and then we process the node itself. So that's how we get an M here. Okay, so now that's done. So we come back here, so we print H. So that's done. We come back here, we print R, and that's done. We come back here, we print E. So we are done with this subtree now. So now we come back here, and we simply make a call to post order on the right subtree, which makes a call to post order on the left subtree, which returns, right subtree, which returns, and then we process the node and we print it. So that's how we get an X here. And then this guy is done, so we go back here. So the only thing that needs to be done is process this node, meaning print it, and we are done with the entire tree. Okay, so that's how we get this particular ordering when we visit the nodes in post order. All right. Okay, so now finally, here's a comparison of the performance characteristics of the different implementations of the symbol table API that we have seen so far, right? So we have looked at a linked list based implementation of the basic symbol table API. We looked at an ordered array based implementation of the ordered symbol table API, and a BST based implementation of the ordered symbol table API. Okay, so search in this case is linear. It's log of n with ordered array because we take advantage of binary search, and with BST it's h. And what is h? Well, h is simply the height of the BST, okay, which is proportional to log n if the keys are inserted in random order, right? So here we're simply saying that search is proportional to the height of the tree, which in the average case scenario is log n, and the worst case scenario is n, right? What about insert? In the case of a linked list based implementation, it was a linear time operation, also a linear time operation with an ordered array based implementation, and it's h in the case of a BST based implementation, where h again is the tree height, right? Delete is n here. It's a linear time operation. It's also n here, whereas with hybrid deletion that we discussed, it is a square root of n. Now here, you need to keep in mind that once you start allowing deletions in a binary search tree, the other operations also suffer, right? And they also become operations that have running time proportional to square root of n, all right? Okay, what about these operations? So these are all ordered operations. These are simply not allowed here. We cannot implement ordered operations with an unordered linked list, right? Whereas with an ordered array, we could implement all these operations. So min max is a constant time operation. Floor, ceiling, and rank are logarithmic operations, and select is a constant time operation. All right, an ordered iteration is proportional to n, because here we have to look at all the keys in the symbol table. What about a binary search tree implementation? Well, here again, min, max, floor, ceiling, rank, and select, they have a running time that are proportional to the tree height, okay, which in the average case is log of n, and in the worst case is n. Okay? An ordered iteration here is linear as well. Okay. All right, so that completes this lecture on binary search trees. Thanks for watching.